Hi, this is Shelley Physics, episode on conservation of angular momentum. This is a merry-go-round that's moving at a constant angular velocity. You can see its shape isn't changing, nothing's changing about it, no one's pushing it, it just keeps on spinning on and on. When you put people on it, what's different here is that they can change the distribution of mass around that spinning object. When they move inward, the merry-go-round speeds up, it increases its angular velocity, and when they lean outward, it slows back down. This whole front of the merry-go-round. Now the other thing you can do on a merry-go-round is you can jump onto it as it's spinning. You can have someone push it and make you go faster, and apply an impulse, which causes a change in angular momentum because there's a change in angular speed. Another in sports, there's figure skating, of course, and we've seen some of those figure skaters spin ultra fast, and this is evidently the Guinness Book of World Records fastest spin ever. We'll take a look. She enters the spin with part of her body outward with a little bit of rotation and brings her legs and arms extremities in, and there she's clocking over about 308 revolutions per minute. And I don't know if you've noticed, but this creates sort of an enigma. We just finished up a unit talking about impulse. The net force times time equals a change in momentum. And that it takes a net force to change an object's velocity. Well, there's a problem here. You see, in terms of Newton's second law for rotation, impulse is net torque times time equals a change in angular momentum, I omega final minus I omega initial. You see, shouldn't it take a net torque that's external to the object to cause a change in angular velocity? It should. Same thing should matter, right? But remember, rockets can move. Rockets can change their momentum without a net external force. If we just consider that linear momentum is conserved with rockets, that means they've got an initial mass as well as an initial velocity, and a final mass as well as a final velocity. And of course, we can't forget that there's mass ejected backwards. So there's the mass of that little bit of stuff, but moving at a really high velocity. So this would be a smaller mass compared to the mass of the rocket. But what we get here is this velocity, this velocity, that other stuff, that the fuel that's being ejected is moving really, really fast, but in the negative direction. All right, so that negative direction of velocity of all that mass creates an increase in velocity here, as well as a decrease of the overall mass of the rocket. So it accelerates more and more and more as rockets blasted off, and they're expelling that fuel. Their acceleration rate increases because that mass decreases. So that's how a rocket, something that moves with translational motion, can increase its velocity, its translational velocity, without a net external force. What about the ice skater, though? Here we've got ice skater, the merry-go-round. In both cases, there's an initial angular momentum to the spin. She did apply, with the ice skater, she did apply a net external force to get a rotational motion going. Her skates interacted with the ice to cause that initial spin. And afterwards, how did she increase her angular velocity? On the merry-go-round, how do people change their angular velocity? They bring mass in or move it out. The ice skater brought her legs and arms in to increase her speed. People on the merry-go-round moved inward towards the middle and then back out to slow it back down. So with angular momentum, what we can consider here is that we've got an initial moment of inertia, which depends on distribution of mass from that axis of rotation, and also the initial angular velocity. And that I changes between the beginning and the end. So by bringing mass inward, there's an internal force there. It's not a torque, it's not a net external torque, but just an internal force of moving mass on the object or redistributing it. We get a change in angular momentum. if the I value decreases. So if we bring that mass inward, R values decrease, moment of inertia are of magnitude like something's oftentimes a fraction times mr squared, or for point masses, it's just mr squared. So if we decrease the R, we're going to decrease the I, the moment of inertia. And according to the law of conservation of angular momentum, when the I decreases, that's going to cause an increase in angular velocity from the initial value. That merry-go-round starts spinning faster. All right, so let's look at an example of that merry-go-round. Okay, first example, what if we have a mass, a kid on this merry-go-round, moving inward? Now I can give some values to everything here. We can have the merry-go-round's mass, big M, and radius R. And we got someone out here at the radius, and let's say that they're going to move inward to about 1/4 the radius. It's hard to get, we're not going to go directly to center here, but M is going to travel from, let's say, the radius on the outside to about 1/4 the radius. And let's give a radius to that merry-go-round, 1.2 meters. Let's also give it a mass. Now, they can be kind of fairly massive. Let's go 150 kilograms. And we'll take a 50 kilogram kid. So big M, the merry-go-round is 150, the little kid is 50. All right. Now, law of conservation of angular momentum. I'm going to write it out here. This is our tool. I love it. It's short and sweet. Now keep in mind, this is our system. This is the moment of inertia of our system. So we have the merry-go-round considered here. But what about that kid? Well, I guess we can consider the kid as part of the merry-go-round. Just like if we take, objects like a rocket itself would often break apart into pieces. So you might have the whole rocket as the mass. Its mass is the sum of the parts of the rocket. So piece 1 plus piece 2 would be the mass of the total. So the initial momentum will be the mass of the merry-go-round. Let's consider it a solid disk. Moment of inertia of a solid disk is 1/2 mr squared, if you look that up on your reference page in your textbook. So there's our merry-go-round will be a big M, r squared, plus we've got the moment of inertia of the child on the merry-go-round out here. And for that point mass, it's just little m, r squared. So this is the initial condition where the kid is at r. So overall, our I is 3, I can't combine those. 1/2 times 150 times 1.2 squared plus the little kid, let's see, 50. And the kid's chilling out here at 1.2 meters. So that's our initial moment of inertia. Our final moment of inertia will be when the kid has gone into 1/4 of that radius. So the only thing that's going to change here for the final moment of inertia, the merry-go-round's moment of inertia stays the same. Its shape doesn't change. However, the distribution of mass of the kid on the merry-go-round, that does change. See what effect that's going to have. So the R is going from 1.2 to 1/4 of that, which is 3/10. Let's go ahead and calculate those out. This piece is 108 kilograms meters squared. Now we're going to add on this term to each one of those. All right, so you can see there is going to be a significant change to this system's moment of inertia. It's going from 180 kilograms meters squared down to 112.5 kilograms meters squared. It's not quite cutting in half, but it is changing significantly. So let's plug those in, 180. All right, now I guess we would have an initial rotational speed. If you take, let's just say 1 time around per second, that would be very fast for a merry-go-round. So let's go about, you know, 1/3 of a turn per second. Let's say 2 pi radians over 3. That'll be radians per second. We'll set that as our initial omega. Okay, 2 pi over 3 radians per second. And let's see what we get out of it. Okay, we're popping down to 112.5 is a moment of inertia. So you see here, as the moment of inertia decreases, what should happen to the angular velocity? We should get an increase in that angular velocity. I'm getting a final angular velocity of 3.35 radians per second. You can see that 3.14 radians per second would be a half of a rotation every second. So we're going from about 1/3 of a rotation per second to about 1/2 of a rotation per second. So that's a speed up, and especially when you're on that merry-go-round, it does feel like you get this acceleration feeling in your stomach. Everything's going all kind of funky and wonky. All right, so that's one application of conservation of angular momentum. Now you could look at the ice skater also, the figure skater. Sometimes it's hard to imagine that, but basically you're trying to go from, let's see, this is more of the 2. This is more the final result. You have the person's legs and their arms together. Sometimes they'll put their arms up because it looks more elegant. Okay, something like that. But even so, they've got their mass really close to their body. They're trying to spin. This is our kind of a final condition here. They're moving really, really, really fast. Did that a little backwards. How they start out is, got the core of the person, and their arms are often extended, and often, they have to have at least one leg down, but at least another leg is extended like this. There's an initial momentum, angular momentum going to a final. So we have a starting slower angular velocity transitioning to a faster final velocity. So this is a nice kind of a slow type of motion, and the final one's a lot quicker. So that's another thing you can do. You can look at the person's core and how their mass is distributed for an initial moment of inertia. I might look at a person as in maybe a bar with the axis through the center. Their core probably doesn't have much moment of inertia, but you might look at them as a kind of a solid disc with a very small radius. Their one leg should be really close in, but their other leg, this will have a significant moment of inertia out there. It's kind of like a bar with the rotation axis at the end. So if you simplify a person's body and distribution of mass that way, you can come up with an initial moment of inertia. You pull it in, everything in, that moment of inertia, of course, is going to change. Everything's going to get much tighter and closer in. So that's a scenario you could look at with some numbers if you want, and see how that figure skater could possibly reach that 308 radians per second. What other fun stuff you could do on the merry-go-round? You might recall we're going to use that same moment of inertia of the merry-go-round here of 108 kilograms meters per second. Okay, with that radius of 1.2 meters. All right, let's say this has initial angular velocity of 0. Got a merry-go-round here. Now keep in mind, merry-go-rounds sometimes have these bars that come out, allow people to hold on to them. Okay, and what I'm going to do in this case So I'm going to take a kid, that same kid, on a skateboard with a velocity now. Here there's going to be an initial velocity of, let's go about 5 meters per second. All right, and there's this kid on it, going at 5 meters per second. There's them, little m there. And this kid's going to jump onto the merry-go-round. So we've got a linear momentum here. And when the kid jumps onto the merry-go-round at this point, 50 kilograms that's moving at 5 meters per second is going to transfer onto this merry-go-round. As you can imagine, that's going to start its motion up when that kid does that. So what do we do here? If we've got I omega, or I initial, omega initial equals I final, omega final. See, what's kind of weird here is this kid doesn't have a moment of inertia because he's not part of this rotational system here. So it's kind of weird to think about. And the only thing that does have a moment of inertia as far as a rotating object is the merry-go-round, and it's got 0. So how are we going to get an omega over here that's not 0? Okay, that's a big question. Ooh, that's a big question. How do we get 0 equal and not 0? What that indicates here, if we know that when this kid jumps on the merry-go-round, that must mean the kid has an angular momentum to start with. Just before he jumps on, or she jumps on, whoever it is, the kid jumps onto the merry-go-round, there's a angular momentum to this kid. So we can't really use this form. Instead, kind of like when you look at torque is a force times a torque arm. If we're just looking at the magnitude, it's really R cross F. Angular momentum is, I should make that legit. Here we go. It's a lot better to see it this way. If torque is R cross F, angular momentum, also being a vector, is R cross P. Actually, where we get this from is from Newton's second law. F is equal to ma, but you might recall it's also equal to dp dt. Okay, it's a rate, instantaneous force at a particular time is the rate of change in momentum. And this is where we get F times time equals change in momentum. If you look at the delta P's and such like that. So if we transform this to a torque, we do that by crossing one side. Well, we'd have to do that over here. And you see what is the vector piece of dp dt? It's the P. Momentum is the vector. So this is equivalent to a kind of an R cross dp. And from that, you can kind of see that they're related in this very similar way. And the beautiful thing about this form is that momentum, in this case, is about a mass moving with a velocity. So another way you can write this is L equals R cross mv, where m is a scalar, so the R is crossing with the velocity vector v. The short version of this is when we look at the initial angular momentum of the system with a kid jumping on the merry-go-round and set it equal to the final angular momentum, the merry-go-round has 0 angular momentum to begin with, but the kid doesn't. If we consider an R cross little mv, this is the initial velocity of the kid, we'll call it VO, that's at 5 meters per second. M is the mass of the kid. That's going to be the initial angular momentum of the system. And at the end, they are going to be rotating together as one. So we can set the final angular momentum of the system, the merry-go-round and the kid. I'll make a note of that. This is the merry-go-round plus the kid. Or this is just the kid. Because the angular momentum of the merry-go-round in the beginning is 0 over here. So that's our setup. Setup of our system. Identifying that we've got a point mass that's moving with linear motion that's going to cause a rotation later on. Okay, so first thing my eyeball wants to do is get rid of this cross product. And as we look at this, what's R cross MV? Well, the kid is not going to interact with the merry-go-round until jumping onto it. And at that point, R is pointing out this way, V is this way. So thankfully, the angle between R and V is 90 degrees. Just to get your mind wrapped around the moment we're looking at here, just as with collisions, we would analyze the moment of inertia of a system just before the collision and just after. We're not looking at like the results of afterwards or what was happening before, but the moment before and the moment after, because other forces can interact with that system and change its momentum before and after that occurs. So here we're gonna, since R cross V sine 90 degrees is the same as R cross V, the kid's moment of inertia is just the radius of the merry-go-round times the kid's mass times the initial velocity. And that equals the final moment of inertia of the system. Again, we can reuse that value from the other problem. When they're combined, they're at, that was when the kid moved into 1/4. But when the kid was out at the radius, that was 180 kilograms meters squared. And we should be able to find a final angular momentum of the system. So we're going to go ahead and solve that. R is 1.2. The mass of the kid is 50. The initial velocity is 5. And we'll solve for the omega final. That's 1 2/3, 1.67 radians per second. There it is. The system does start to rotate at about, quarter rotation per second. So there it is. Here we had a rotating system changing its distribution of mass, causing a change in angular momentum. And here we have a system that can rotate. It was at a 0 spinning speed at first, with a kid with translational momentum jumping on and attaching, becoming part of that spinning system. So we considered his or her momentum just before jumping on to be an angular momentum. Conservation of linear momentum and conservation of angular momentum, they always work, always true. If you're ever asked the question, does the translational momentum of the system change, or does the rotational momentum of the system change, the answer is always no. So just keep that in mind. Easy question to answer. Conservation of angular momentum and translational momentum are always true. They're always going to be true. So that is the end of this episode.